have degree 1 monomials, and we introduce one variable for them, so some y1, and similarly in the first column. Then on the diagonal, because of the idempotence, we know that the x1 squared is actually the same as x. So we again introduce these yi on the diagonal. And then in some general cell of this matrix, in some I position I j, we just put y I j, so that's the equation of xi xj. And because of this symmetry and positive semi-definiteness, we immediately get that y I j and jy should be the same. So this is the relaxation. We know from Tony's lecture that this minimum is, well, this really is the relaxation, but now our exercise is to prove that under these particular constraints, this minimum already equals this. So
here you don't use x star, xi star equals xi. How you use it?
I don't think I use it. So it's one that's in my view it's just this usual assumption in the problems. I guess it is hidden in the theory by the fact that they are self-adjoint. Positive semi-definiteness. They're self-adjoint. All of these expectations, even though our vectors are over C, and for the solution to our exercise, it would suffice to, from this data, from the optimizer here, to cook up a value, some set of psi and xi here that achieves the same value. And you know that actually, before I do that, I should argue that the minimizer here exists, that the minimum is attained. That's because this is a slice of the spectrohedron close. Or rather, this is the slice of the positive semi-cone, so it's spectrohedron, so it's close. And I can argue that it's bounded because of this positive. In particular, I need to have positive 2x2 principal minors. And these 2x2 minors, for example, if you look here, these 2x2 minors look like 1 yi, so I know that determinants are non-negative, and these determinants turn out to be i times 1 minus I. So this one really forces each y to be in the physical set here about it. So I can presume that I am given some scalars y1, yn, and yij, and I will use them to cook up a vector psi and matrices x1 up to xn, such that they really achieve these values. So I want to create this data such that.
Sorry. So why do you have a symmetric matrix here? So in principle, you should have yij and yji.
Yeah, there should be a yj. So if I view these now as representing the expectations, I can prove that the xi, xj is the same expectation as xj. Because number one, these operators, they take real values because it's self-adjoint. So all the values are not real, so it will the expectation. And I come psi into xi xj, and let me take the adjoint of this. I star xj star or psi. Jonas, this is the same. Actually, here the.
Oh, you use it here.
So our goal now is to, from this data of the minimizing of the relaxation, create psi and x1 up to xn such that the following is satisfied. Well, these conditions essentially. So psi star of psi is one. Well, rather, I want to create them such that these conditions are achieved, and additionally, I have psi star of psi is my given yi, that's some real scalar that I was given from the minimizer, and psi star of psi is j psi is yij. I want to prove that these values really are attained by some collection of projections. So let me state two lemmas, which I will use. In the interest of time, I will not prove them, but if in case of man, I can. Lemma one, I can claim that these two conditions, self-adjoint and impotence, I can give them a very nice geometric interpretation. So these two conditions together, they are equivalent to x is orthogonal projection onto some subspace. This let's see, like a matrix. And I claim that these two conditions are equivalent to x being the orthogonal projection onto some subspace, and orthogonal with respect to the first one. Is that M is Hermitian. Then I can do the Cholesky decomposition. So M equals L star L for some square matrix L, not necessarily for rank. With these two lemmas, what I will do is I will take this positive semi-definite matrix and I will decompose it as such. I will write M is L star L, where I will denote the columns of L as L0 up to M, and an equivalent way of writing this decomposition means that the ijth entry of M is just the scalar product of Li. With this, I now prescribe my psi and my xi's as psi being just L0 and xi being the projection onto the space spanned by Li. And it is possible in here that some LIs may be zero, so that the projection onto and now we'll verify that the conditions and these values are all satisfied. So let's go one by one. So first of all, psi is a unit vector. That is true because pairing L0 with L0 should give me the 0, entry M, which is 1. Satisfied. Now, these two are satisfied because of lemma 1, because I prescribed xi as projections onto some. Satisfied, so now I just need to verify these values. For that, I claim that xi psi is, Li. This isolate cases, possibility number one, Li was zero, then Xi was the identically zero map, and this condition holds. Otherwise, Li was not zero, so it's found a one-dimensional space, and then the projection, an explicit way to write it is that it maps any vector v to a multiple of ui, and the scalar that determines this multiple is given by pairing ui with v and dividing by. In this case, if I now put in psi, which is L0, and also sorry, I'm mixing up my notation. I get a pairing of Li, L0. That's the I0th entry of M, which should be just Y, I. Similarly, the norm of Li squared should be the ith entry. So again, yi, and because I'm saying Li was not zero in this case, I know that yi is not zero. I indeed get that this projector maps L0 to Li. Now I'm almost done because I'm running out of space on the board. To check this value, I write I star xi psi. I know that xi is idempotent and self-adjoint, so it doesn't make a matter if I now introduce another xi star in here. And this is now just the scalar product pairing xi psi with itself. But we know that xi psi is just ith entry of the matrix. Yi, and quite similarly, in this expression, I get introduced star in here for free, and that introduces again to a pairing of Li and Lj, so the ijth entry. So we cook up psi and xi such that they achieve these values, so then it's immediate that the objectives are the same. So
Okay, good. So maybe you are in the group, you have something to add? You have something to add in the group?
Well, we have one question that we. But they said that the same argument should be valid for high.
You have to extend the relaxation degree.
That's you mean.
How to prove that you can also extend higher degree polynomials.
To extend this, what does it mean?
Argument holds if you look at P of x1, higher degree polynomials of the trigon.
Yeah. But I guess here you need to go to higher order moments. Why to have moments which are not constrained? That's practical terms. You have a matrix of moments which are practical.
So I think the point is that you don't because of the.
So how you constrain the Y which are not fanatic?
I agree with you. In the proof, it just says in the last sentence, it says with similar.
Maybe. Nice, yeah. What? Yeah. Okay, good. So
our problem is about linear programming with entropic regularization. So again, let me write this problem again. So I'm using the correct vector spaces already because then I don't have to insert. Can everyone see? Okay, so this is our cost function, our entropic regularization function, and then we have the usual constraints. I will omit x large 0 because this is already in here. Where A is okay. So if you remember, this was an example in Simon's talk. And to give it motivation, Simon gave a very nice motivation of what this could be. So this is now a linear, or can be seen as a transport problem, and we can encode this the problem in such a statement. For example, it could be a transport problem where we want to transport things from two locations onto a set of other locations. Okay, and we say, okay, there's a number of goods at INRIA, there's a number of goods at UIT, and we want to transport these goods to CWI in Amsterdam, Trento, and ICFO. And we denote the number of goods that is transported from INRIA to CWI, X1, and equivalently for the others. And now you can identify what's going on here by realizing that we have a few constraints. So for example, obviously, that's our condition. The stuff that was once at INRIA needs to be transported to these locations. So we have a condition that reads x1 plus x2 plus x3 equals something. So I'm now using the same numbers that Simon has used. So this is the condition that everything is moved. Then we have x4 plus x5 plus x6 equal 51, the same condition that UIT has moved everything. And then we have conditions that essentially depend on the goods that are moved to the locations from the sender locations. And these are the conditions x1 plus x4 equal, in this case, 36, x2 plus x5 equal 26. And then we have another condition, but this condition is actually a redundant condition, but we can still solve it. So I will now leave a blank space here. This will be algorithmically clearer in the next, when we present the code. So this is our problem. And essentially what this here means is this gives us the AX times B constraint. This is exactly how we come to a problem like this. And now obviously there's costs associated to transporting this, and this is encoded in this matrix W. So to state this more formally, okay, I'm not writing out the matrix A, it takes too much time, but B will be this constraint, and then we have W Okay, our cost function. And now the question is, how can we solve such a problem? And in the lecture, we have seen that we can encode. So for a matrix A, we can define a toric variety. And what we would like to have is that when moving, maybe I still, okay, I do not have the picture that Simon showed, but the idea was we have a feasible set that looks something like this. So this would correspond to this constraint. And then we have a path in the set that goes to our feasibility polytope or region, which is encoded in A and B. And the idea is that we follow this path, and this path is exactly given as our toric variety. So we want to optimize, we want to follow this toric variety into our feasibility set. And the idea is that we check the feasibility in the end by projecting with our matrix such that each point on our variety, which is a point X, will be equal to B exactly. Sorry, this is B. Exactly at this point, and here we'll have something like xi for the ith iteration of our program. Okay, and this is what we try to do now. We do this in OSCAR, so we have our matrix A, we have our matrix, vector omega, which is the cost function. We have B, we have a regularization parameter. So this was the first example. Then there's, let's say, a subtlety, because in order for this to converge, we need to make sure that this last condition actually, we need to extend this matrix A such that the problem is well posed, meaning that there's also a solution for this here, and this is what these few lines do. So this is, let's say, a subtlety to make our problem convergible or convergent. What we would like to study now is how does our program, this linear program, behave for different epsilon. So we choose different epsilon here. And as you remember, these different epsilon, they essentially tell you how close you are to the unregularized problem. And we choose a list that goes from 0.025 to infinity. We found that smaller values, they lead to a problem. We put this all into a list. So what we do is, okay, I will maybe only go to the, actually at this point you can talk about. So there's a condition that Francesco will elaborate a bit on, which tells us that for each point in our iteration, we actually stay on the variety. So we move, we have different iterations, we move on the variety, and at each point we want to be sure that indeed we are on the variety. And there's an iterative condition that Francesco can tell you something about. And then at some point we have a convergence criterion that tells us, are we indeed in a region that is our feasible set to a certain tolerance. And I just want to show you some results because we don't have much time. So what you see here is the error or a log linear plot and the iterations and the error we accumulate. And in the legend, you can see these are the different epsilon we've chosen. And what you see is that there's infinity and 0.025 are essentially the same color, but what you should see is if we have like very large epsilon, you can see that the dependence of the error as respect to the iterations, number of iterations, is much decreases much stronger. So the convergence, at least for these cases, is better in some way. But then we can also look at the convergence of the solution. So the solution is now a vector in R6, and we look at, for example, just x1. What means that we look at the number of objects that were transferred from INRIAS to CWI. Now what you see is, first of all, these graphs, they have different length, but this is expected because The number of iterations will be different because for the different, there will be different, so the convergence threshold is the same, but for different regularization factors, this will just turn out to have different iterations. So for example, if I choose an regularization that is infinity, that means I only need, I think, 20-something iterations to reach my convergence threshold, whereas for very small values, so these are 0.01, 0.05, 0.05, and 0.025, we need a higher number of iterations. And this just also tells us that actually the converged result of this is different, which makes sense because we're using a regularization. But overall, you have to also note that now we look at just one value. Obviously, we need to look at the, let's say, the error of the whole solution vector. Okay, maybe now it's a good time to, yes, for Francesco to tell you something about how we can assure that we stay on this.
Can you all hear me? Okay, good. Thanks a lot, Otto. And how much time do I have? Like 1 minute and a half, probably.
I think -5.
Now it's 3 minutes.
So how much? Okay. 3 minutes, okay. I will quickly show you some part of this problem here, algorithmically. So we have this minimization problem. This is a convex optimization problem, has a unique solution when asking x greater or equal to 0 here. And I recall you from Siemens' lecture, this is equivalent to solve the following. So fix epsilon. Okay, and I want to solve that problem of the regularized linear program. Let's call this maybe entropic linear program. Okay, so this is equivalent to solve the following. So we ask x to belong to exp of minus 1 over epsilon w. Okay, this is multi-index notation. So this is e to the power w1 times e to the power w2 and so on. Star with ya. This is a scale Tori variety. We ask ax to be equal b and also x to be positive. And this is precisely rewriting the problem over there. So this has a unique solution as a convex optimization problem. And what I would like to show you is basically how the algorithm works. So we're building a sequence, and we would like to see that this sequence converges to the unique solution for a fixed epsilon. Now, usually when you do this using some algebraic geometry method of any kind, you could end up having like many solutions of this problem here, and then you need to select manually the only positive one. So the advantage here is that we can have an iterative algorithm that tells you every time the unique positive solution. Is it positive or non-negative? Positive, yeah. Okay, so here is the sequence that leads the algorithm. So we start with this initial point, x0 of the sequence, and we define this to be exp of minus 1 over epsilon of w. And then we define x k plus 1. So at the k plus 1 step, this is defined to be component-wise. Okay, let's do this component-wise. This is xi, k, so previous iteration, times b to the ai, and I divide by a xk to the power ai again, 1 over c. Okay. Now there is a nice theorem, just to mention. I will not prove this, but I will just prove that actually every point in the sequence will stay in this variety over here. So we are sure that we have a unique, so we end up with the unique, with a unique point at every iteration. And so the theorem is the following, okay? The solution to entropic linear program that Otto previously wrote down over there. Okay, with B in int of the cone of A. Is the unique is the unique limit point of this sequence. Of the sequence xk. Okay. Now, very quickly, I conclude very quickly, maybe. Okay. In 10 seconds. Okay, so yeah, but 10 seconds I have more, right? Now, just to show you the idea behind it, how do you show that this keeps on staying on this variety over here by each iteration? First, you need to assume a technical assumption, okay, that I forgot to tell you that is satisfied over there, is that every column sums to a constant C. And second, you need to have, like, by induction, you show that first this belongs to this. You just replace, you just see this because at the point in the toric variety 1, 1, 1, 1, 1, you have precisely that x0 belongs to the toric variety, to this scale toric variety, sorry. And for the inductive step, you just look at the logarithm of this. So you end up with something of the form log of x k plus 1. And since this is a product, you split the logarithm. This is log of x k plus something, which actually belongs to the row span of A. So you can just expand this here and see that this belongs to plus some row of A. You apply the exponent, and you will see that this is equivalent to say that xk plus 1 belongs to, also this one is, what was it? This is also minus omega over epsilon plus rho of A. Sorry, belongs to this set here. So this belongs to minus W over epsilon plus the row space. So exactly. So no, sorry. And so on. Okay, just concluded by yourself exercise.
So this is to show that indeed the iteration walks over the point, right? You can see from the iteration that if one point B equals to x, then you have a stationary point.
So here I'm going to show you how we implemented this problem and solve it with some SDP solvers such as CSDP, Hypatia. So here, as a first step, I'm going to declare my model as I want like to use CSDP as an optimizer here. In this case here, I am going to declare like my variables y, which are the moment variable, up to degree 2t, which is the t, where our t here is our relaxation. And then I am going to impose that first I have the first constraint, which should be, which is y0 should be equal to 1. And here, right now, I'm going to declare my moment matrix. So which all coefficients will be taking the yij yi plus j, and the constraint for that matrix should be in the PSD cone. The same thing for the localizing matrix. As Matteo mentioned here, that we are going to defining that matrix by representing the moment matrix and subtracting the second block. And also we should declare it as a PSD matrix. And of course, here we should mention that if our degree is bigger than the relaxation multiplied by 2, relaxation degree multiplied by 2, so we should have an error. And then our objective function will be the sum of these moment values, moment variables, and we are going to minimize it. And so I'm going to show you. So here we are going to do the experiment for a relaxation degree t equal to 50 and the degree of the polynomial is equal to 100. Okay, so here we can see like for CSDP, this is the optimal value that we obtain. And I can show you the moment matrix that we have obtained here, which is in this format. And I can show you here the singular value decomposition for this to see like it has rank 1, which is rank 1 matrix. So you can see here, these are all the singular values of this moment matrix, and you can see here that the first singular value is around 10, and the others like are around like 10 minus 9 up to 10 minus 15. So we can see here that our matrix here is of rank 1. And yes, and we did the same. We did the same thing using the moment polynomial out package. Yeah, sorry.
No, we increase the order if we need it, but it converged on the first level.
Yeah.
So the certificate that we got solution on the first level of the hierarchy, we didn't have to move the relaxation order any higher.
Yeah, okay. And so we did the same thing for the, yeah. Yes. Okay, actually we present this in the graph like we can read it. Just 1 minute, sorry. Yeah.
At the moment,
If you scroll up to the moment.
Yeah, it should be this one. And I can, if you want, like,
There is the first moment. Give you the.
yes. And these are the moment values of our, the optimal moment values in our case. So this is y0, and then the first moment, which is equal to 0.9, which is the minimizer here. Yeah, exactly. And we kind of showed this in the graph, like we just show this in up to degree 6, and you can see here that we expect to have like one minimizer. Yeah. And we can see here that like if we have like an even degree, so we just it collapse. Yeah. And as I said, we did this same. We did the same thing with the moment polynomial package, and we managed to extract the direct measures like the weights and the point for that for this experiment, and this is the weight, and this is the CI, which is the point of the direct measures, which corresponds to the first moment that we obtained. Yeah, that's it.